All right, so since this matches with this perfectly, we have it being the partial with respect to y of the partial with respect to z of our scalar function f. Now, we actually haven't done the problem yet. We have to find our f, but the f is not going to be too difficult to find. Okay, so we're going to take, let's write out what p, q, and x are, p, q, and r are again. Okay, so actually let's do it over here. So our p of x, y, z, which is the partial with respect to x of our scalar function, is y squared z plus 2xz squared. Okay, so we're going to take and we're going to integrate that, or take the antiderivative with respect to x. So we're going to take the antiderivative of p with respect to x. That's going to be y squared z plus, I don't know why I'm doing y squared z, there should be an x there, y squared zx plus, now here we're integrating with respect to x. So the integral of 2x is x squared. So we're going to have x squared z squared. Now, I'm going to write the next piece. It's some function. Let's write it, say, as g1. And it's going to be a function of y and z. Okay, because we've integrated the x person. So this is a constant with respect to x, but there's still y and z going on, right? Let's take a look at q. Q, remember, is the partial of f with respect to y. So we're going to take, remember, our q in this case is 2xyz is the partial with respect to y of our unknown as of yet scalar function f. Okay, so taking the integral of q with respect to y, that's going to be, so we're integrating this with respect to y, so you're going to have a y squared, and the 2 in the denominator is going to cancel with that, so it's going to be x y squared z plus some unknown function, we'll call it g2, of x and z. Now, one thing I want you to notice, we have an xy squared z here. Actually, we have an xy squared z here too, right? So that's something we should expect to have happen. If we have a term that includes all three variables, it should match. Okay, this x squared z squared, well, that gets sucked into that g2. All right. Next, r of x, y, z. That should be the derivative with respect to z of our f. So in this case, our r is xy squared plus 2x squared z. Okay, so let's take the integral of r dz. Okay, the integral of r dz is going to be, or is equal to, x y squared z plus, integrating this with respect to z, it's going to be x squared z squared plus, and now we have some unknown function of x and y, as we integrated out the z. So now, all three of them have this x y squared z term. Let's highlight. So all three of them have this x y squared z term. These two have the x squared z squared, and then there's no, everything else is put into like a function. So our f, our scalar function, is x y squared z plus x squared z squared. And we may or may not put a plus k on there, okay? I'm going to go ahead and put it on there because, you could have an actual constant, right? The derivative with respect to a constant is 0, okay? Some books, they don't put them in there because then they just say, well, that means this is equal to something, whatever. But we're going to put on the k there, okay? So we'll leave that there, and that's the function. Now, we could go even further, okay? We could integrate this, integrate the vector field, okay, we can integrate this vector field along the curve. And our curve is C, which is given by x equals the square root of t, y equals t plus 1, and z equals t squared, where t goes from 0 to 1. Okay, so fundamental theorem of line integrals. The first part, okay, states that this is just going to be f of r of 0 minus f of r of 1 minus f of r of 0. Okay, well, what was our function? Our function was up here. Okay, let's take r of 1 and r of 0. R of 1 equals the point 1, 2, 1. R of 0 is the point 0, 1, 0. Okay, so we're going to have, now here we don't need the k because it'll cancel, just like any other definite integral. Okay, so we're going to have xy squared z plus x squared z evaluated from 0, 1, 0 to 1, 2, 1. That's going to be 1 times 4 times 1 is going to be 4 plus 1, 5 minus 0. So we get 5 back. All right. See you guys next time. We're going to go into 13.4 next.